Math is full of counterintuitive facts. Facts like between any two real numbers you can find a rational number, or that Gabriel's horn is an object that has finite volume but infinite surface area, or that a conditionally convergent infinite sum can be rearranged to equal any real number that you want. In fact, regular viewers of my channel probably know that I have an entire series of math facts that sound fake but are actually true, a playlist of which I'll link at the end of this video. One such counterintuitive fact is that the number 0.999 repeated is actually equal to the number 1. For many people, this might seem like a ridiculous claim, because surely 0.999 repeated is the number just before 1 on the number line. That is, it's the number that's closest to 1 without being 1. Well, in today's video on Scholar Sauce, we're going to offer 5 proofs that 0.999 repeated is actually equal to 1. And unlike this finger right here, all the proofs work. Number 1. While it might seem like a bizarre claim to say that 0.99 repeated equals 1, most people would agree that 1/3 is equal to 0.333 repeated. However, if we simply multiply both sides of this equation by 3, we get 3 times 1/3 must be equal to 3 times 0.333 repeated. But 3 times 1/3 is 1, and 3 times 0.333 repeated is 0.999 repeated, and hence 1 equals 0.999 repeated. Personally, I find this argument quite rational. But perhaps that's not as convincing to some of you, so let's try again. Number 2. This time, let x be equal to 0.999 repeated. Then multiplying both sides by 10, we get 10x is equal to 9.999 repeated. Notice that since we have an infinite number of 9s after the decimal point before multiplying by 10, we still have an infinite number of 9s after the decimal point after multiplying by 10. But then we have that 10x is equal to 9 plus 0.999 repeated. But that 0.999 repeated is just x again, and so we have that 10x is equal to 9 plus x. Well, subtracting x from both sides, you get 9x equals 9, and then dividing by 9 on both sides, you get x is equal to 1. Well, since x was equal to 0.999 repeated to begin with, this means that 0.999 repeated is equal to 1. Well, I think that argument was 10 times better than the last one, but let's take it up a notch anyway. Hey, I once failed a calculus exam because I was seated between two identical twins. It was really hard to differentiate between them. And if you like that joke, hit that subscribe button. And if you didn't, hit the subscribe button anyway, because we want you to be part of the Scholar Sauce community. All right, let's get back to the video. Number 3. This proof relies on the ideas of a geometric series. A geometric series is a sum of the form S is equal to A plus AR squared plus AR cubed, and so on, where A and R are real numbers. Since this is an infinite sum, we can find out if it converges by looking at the sequence of partial sums. Let S sub n be the partial sum of this series that adds the first terms up to a power of n. That is, S sub n is equal to A plus AR squared plus all the way to AR to the n. But then we can factor an R out of all of the last terms, and we get that S sub n is equal to A plus R times the quantity A plus AR plus AR to the n minus 1. Now we'll do a little trick here and add in a 0 in disguise. That is, we'll add in AR to the n in the parentheses and subtract it out. But the first terms in the parentheses is just S sub n again, and so we get that S sub n is equal to A plus R times S sub n minus AR to the n. Distributing the R yields that S sub n is equal to A plus R times S sub n minus AR to the n plus 1. Subtracting the R S sub n to the other side, we get S sub n minus R times S sub n is equal to A minus AR to the n plus 1. Factoring out the S sub n on the left and factoring out the A on the right yields the quantity 1 minus R times S sub n equals A times the quantity 1 minus R to the n plus 1. And hence S sub n is equal to A times the quantity 1 minus R to the n plus 1, quantity closed, divided by the quantity 1 minus R. But note that we can only do this step if R is not equal to 1. If R were equal to 1, then the previous equation is just the vacuously true statement that 0 equals 0. Now we need to include ideas of what it means for an infinite sum to converge. In this case, if S sub n, the partial sums, approaches a number as n goes to infinity, then S equals that number. That is, S is equal to the limit as n goes to infinity of S sub n, as long as the limit exists. The only n in the formula for S sub n is in the exponent for R to the n plus 1. This number will go to infinity, or at least blow up in absolute value if the absolute value of R is greater than 1. But it goes to 0 if the absolute value of R is less than 1. In that case, since as n goes to infinity, R to the n plus 1 goes to 0 because the absolute value of R is less than 1, then this will equal A divided by the quantity 1 minus R. And hence, if absolute value of R is less than 1, we have that A plus AR squared forever is equal to A over 1 minus R. Now consider the number 0.999 repeated. We have that 0.999 repeated is equal to 9/10 plus 9 900ths plus 9 thousandths, because that's the digit that's in each of those places, and this sum goes on forever, and that's equal to the quantity 9 tenths plus 9 tenths times 1 tenth plus 9 tenths times 1 tenth squared, and so on. And hence 0.999 repeated is a geometric series with a equal to 9 tenths and r equal to 1 tenth. Since the absolute value of r is less than 1, we know that this series converges and produces a over 1 minus r as a sum. That is, 0.999 repeated will be equal to 9 tenths divided by the quantity 1 minus 1 tenth, which will equal 9 tenths divided by 9 tenths, which is equal to 1. And hence 0.999 repeated is equal to 1 again. This argument requires some knowledge of calculus, specifically what a limit is and what an infinite sum or infinite series is. This is also probably the most traditional proof of this fact, though it would almost certainly have driven ancient Greek mathematician and philosopher Zeno mad. But I'm not worried. With how he walks, he would take forever to get to a computer to watch this video anyway. Number 4. For this one, let's define some notation. Let's let 0.9 sub n be equal to 0.999 until you have n nines after the decimal point. That is, 0.9 sub 0 is just the number 0, 0.9 sub 1 is 0.9, 0.9 sub 2 is 0.99, and so on. Note that 0.9 sub n is equal to 999 repeated for n nines divided by 10 to the nth power. Well, 999 repeated until I have n nines is just 10 to the n minus 1, and so this fraction becomes 10 to the n minus 1 divided by 10 to the n. And simplifying this, we get that 0.9 sub n is equal to 1 minus 1 tenth to the n. And again, using the idea of a limit from calculus, it's pretty clear that the limit as n goes to infinity of 0.9 sub n is equal to 0.999 repeated. But on the other hand, the limit as n goes to infinity of 1 minus 1 tenth to the n will equal 1 minus the limit as n goes to infinity of 1 tenth to the n. And the limit as n goes to infinity of 1 tenth to the nth power is equal to 0. And hence you get 1 minus 0, or just 1. And hence 0.999 repeated is equal to the limit as n goes to infinity of 0.9 sub n, which is equal to the limit as n goes to infinity of 1 minus 1 tenth to the nth power, which is equal to 1. And so we get 0.99 repeated equals 1 again. All this talk about limits and infinity reminds me of a joke. An infinite number of mathematicians walk into a bar. Hey! Number 5. This last argument is built on one of the erroneous ideas that might cause this confusion in the first place, that 0.99 repeated is the number immediately before 1 on the real number line. We will show that this cannot be the case because such a number doesn't exist. First off, given any two real numbers, no matter how close they are, you can always find a real number between them. For example, if x and y are real numbers and x is not equal to y, then the average of the two numbers, the quantity x plus y divided by 2, is a real number that's strictly between these two. That is, x is less than the quantity x plus y over 2, which is less than y, and hence is a number closer to y than x. So there is no such thing in the real numbers as a number that comes immediately before another number. This means that 0.999 repeated is not the number immediately before 1 because there isn't such a number. But it also doesn't quite prove that 0.999 repeated is equal to 1. Let's take this a step further to get there. To do that, let's show that if you assume that 0.99 repeated and 1 are different numbers, then this will lead into a contradiction of logic and hence cannot be true. Suppose hypothetically that 0.999 repeated is not equal to 1. Then there's a number x strictly between 0.999 repeated and 1. For example, you could just take the average of the two numbers. This means that 0.999 repeated is strictly less than x, which is strictly less than 1. Well, what is x's decimal representation? Suppose we wrote it down as x is equal to 0.a1, a2, a3, a4, where the ai are the digits in that representation of the number. Since x is not equal to 0.999 repeated, it must be that at least one of the ai's is not 9. But the only options for the ai is a digit less than 9, and hence x equals 0.a1, a2, a3, and so on has to be strictly less than 0.9999 repeated, which contradicts the fact that we knew that it was larger. The hypothetical that led to these contradictory conclusions was that 0.999 repeated was not equal to 1. Thus, we have to reject that fact because it leads to a contradiction, and we conclude that 0.999 repeated is actually equal to 1. Well, what do you think? Did you find any of those proofs convincing? Let me know in the comments which one was your favorite and whether you have a different proof that I didn't list. At the very least, I hope that we increased your affinity for the number 0.999 repeated. It may not be your favorite number, but it's always going to be number 1 in my book. If you enjoyed this video, give it a like and subscribe to Scholar Sauce. For other counterintuitive facts, you'll find here the playlist I promised of math facts that sound fake but are actually true. Or you can click here for the first video in my series describing every type of math there is. And thanks for watching Scholar Sauce, and we'll catch you next time.